Okay, let's take a look at how we decide whether a simple covalent molecule is polar or non-polar. The first step that needs to be done is to look through the cross and dot, and from the cross and dot to be able to have an idea of the shape of the molecules. So like in the case of water, we know it is bent, so it has two lone pair. Actually, once we form out the shape of the molecule, the next step that we do is to study each of the covalent bond and decide whether the bond is polar. And if it is polar, we will have to determine the direction of the dipole moment. Let's take a look at how we do that. So in the case of water, oxygen is more electronegative than hydrogen. Therefore, because of this, there will be a dipole moment that is directed from hydrogen towards oxygen. And in this case, both the dipole moment are equal, but they don't cancel each other out. Hence, this is actually a polar molecule because the dipole moment did not cancel out. Next, let's take a look at carbon dioxide. In the case of carbon dioxide, carbon has zero lone pair, two bond pair, so shape is linear. Oxygen is more electronegative than carbon. So this is the two dipole moment that is being drawn. They are exactly equal and identical, therefore they will cancel each other out. Hence, because of that, the dipole moment is zero. So this molecule is non-polar. Let me circle them. And typically, we will label the oxygen which gains electron as delta minus, and the carbon that loses electron to be delta plus. Similarly, for the case of water, your H is delta plus because electron is lost to oxygen, which becomes delta minus. Let us now take a look at the ICl3. ICl3 has got two lone pair, three bond pair, shape is T-shape. And as you can see in the dipole moment, chlorine is more electronegative than iodine. So these two dipole moments are equal, they will cancel each other out, but this will not be cancelled. So therefore, because of this, you will find that the molecule is polar. All right. And in this case, we can label this as delta minus, delta plus. Let's take a look at this pair of molecules. With the presence of actually a pi bond, the pi bond restricts the C to C to rotate. These two molecules are therefore planar. And the next thing to know is that the electronegativity between carbon and hydrogen is comparable, although carbon is slightly more electronegative. But in this case, what we need to focus on are the chlorine atoms, which is actually way more electronegative relative to carbon and hydrogen. So these are the two dipole moments, which we know that in this case doesn't cancel out, but in the context of this, they both cancel out. Hence, because of that, this is actually a polar covalent molecule, while this is actually a non-polar covalent molecule, and we will box this up. Okay, we'll now take a look at these two molecules together. This will be a methane, this will be a chloromethane. Similarly, we will know that as far as Cl is concerned, it's more electronegative than carbon and hydrogen, so the dipole moment is drawn in this direction. We also want to note that actually, as far as alkyl group is concerned, so bear in mind, all alkyl groups is known to be electron releasing. So this group will be releasing electron towards chlorine or donating electron towards chlorine. So this will be delta plus, this will be delta minus. And therefore, because of this, this molecule is polar. In the context of CH4, the C to H bond is little polarized because carbon and hydrogen's electronegativity is comparable. And in this case, you also need to note that although carbon is slightly more electronegative, all these four dipole moments will actually cancel each other out. So therefore, because of this is actually a non-polar covalent molecule. All right. Okay. Last but not least, we look at sulfuric acid. In the case of sulfuric acid, this will actually definitely results in the dipole moment towards O. So this is delta plus, delta minus, and delta minus, delta plus. So this molecule definitely is polar.